Let's do foundational exploration of quantum information science. As we begin, we must contextualize why this field has transitioned from an academic curiosity to a global technological imperative. For decades, the classical computing industry followed Moore's law, the observation that transistor density doubles roughly every 2 years. However, as transistors approach the scale of individual atoms, we encounter fundamental physical limits where classical binary logic no longer holds due to quantum tunneling and thermal fluctuations. A quantum computer is not merely a faster classical computer. It is a device that uses the laws of quantum mechanics, specifically superposition, entanglement, and interference, to perform massively parallel operations. To understand its role, consider the analogy of the microscope. 17th century microscopes revealed a hidden universe of single-cell life that was previously unimaginable. Similarly, quantum computers serve as a computational microscope, allowing us to simulate molecular interactions, optimize complex logistics, and factor large integers in ways that are fundamentally inaccessible to classical deterministic physics. We are moving from the era of digital certainty to an era of quantum probability, and this lecture will equip you with the mathematical and physical tools to navigate this new frontier. Before we can discuss qubits, we must master the mathematical language of the subatomic world. Quantum mechanics is formulated over the field of complex numbers, C, rather than the real numbers, R, which we use for classical probabilities. A complex number z equals a plus bi provides 2 degrees of freedom, the real part a and the imaginary part b. This allows us to represent a quantum state not just as a magnitude, but as a phase on the complex plane. The squared magnitude of these complex amplitudes, the magnitude of z squared, gives us the actual probability of a measurement outcome. This is the essence of the Born rule, which we will discuss later. Why do we need complex numbers? Because they allow for negative and imaginary amplitudes that can cancel each other out. This is the mathematical basis for destructive interference. While classical probabilities always add up, example 0.5 plus 0.5 equals 1, quantum amplitudes can sum to 0, example 0.5 plus negative 0.5 equals 0, allowing us to effectively delete incorrect computational paths. The stage upon which quantum computation is performed is the Hilbert space. Formally, for our purposes, a Hilbert space is a finite-dimensional complex vector space equipped with an inner product. To navigate this space, we use Dirac's bra-ket notation, which is the standard shorthand in the field. A ket, written as bra-psi, represents a column vector of complex numbers that describes the state of our system. Its dual, the bra-psi, represents the conjugate adjoint of that vector, written as a row. The inner product, denoted bra-phi psi, is a complex scalar that represents the projection of one state onto another. If the inner product is 0, the states are orthogonal, meaning they are perfectly distinguishable, like the 0 and 1 of a classical bit. All valid quantum states must be a unit vector in this Hilbert space, meaning their total probability, bra-psi psi, must equal exactly 1. This normalization is a strict requirement that we must maintain throughout our computational operations. In the quantum world, physical operations are represented by linear operators, which we can think of as square matrices. When we apply a quantum gate to a qubit, we are essentially performing matrix vector multiplication. However, nature imposes a significant restriction. The evolution of a closed quantum system must be unitary. A matrix U is unitary if its Hermitian adjoint, U dagger, is also its inverse, U dagger U equals I. Unitary transformations are critical for two reasons. First, they preserve the norm of the state vector, ensuring that the total probability remains 1 throughout the computation. Second, they are reversible. This means that for every quantum operation, there exists an uncompute operation that can perfectly restore the initial state. This is a stark departure from classical logic gates like AND or OR, which are inherently irreversible because they discard information. The entire field of quantum computing is built upon 4 fundamental postulates that act as the axioms of the theory. Postulate 1 establishes that a quantum system is fully described by a unit vector in a Hilbert space. Postulate 2 tells us that these vectors change over time via unitary matrices. Postulate 3 introduces the concept of measurement, which is the only way we can extract information from the quantum world, though doing so collapses the state. And finally, Postulate 4 describes how qubits combine to form larger systems. We use the tensor product, tensor symbol, to represent composite systems. This is the most powerful postulate for computer science. While adding a bit to a classical computer increases its memory linearly, adding a qubit to a quantum system increases the dimensions of our Hilbert space exponentially. This exponential growth is why quantum computers can potentially solve problems that would require a classical computer the size of the known universe.
In classical computing, a bit is a switch that is either off, 0, or on, 1. In quantum computing, our basic unit is a qubit. A qubit is a physical system that lives in a two-dimensional Hilbert space. Its basis states are labeled as ket 0 and ket 1, which might correspond to the spin of an electron or the polarization of a photon. However, thanks to the principle of superposition, a qubit can exist in a linear combination of both states simultaneously. The complex numbers alpha and beta are not probabilities, they are amplitudes. When we measure the qubit, the probability of finding it in state 0 is absolute value of alpha squared, and the probability of finding it in state 1 is absolute value of beta squared. Until that measurement occurs, the qubit holds both possibilities in a delicate, wave-like balance. To help visualize the state of a single qubit, we use the Bloch sphere. Because the qubit vector must have a length of 1, we can map any pure state of a qubit to a point on the surface of a unit sphere. The north pole represents the ket 0 state, and the south pole represents the ket 1 state. The angle theta determines the weight of the superposition, how close we are to 0 or 1. The angle phi represents the relative phase, the quantum secret sauce that determines how this qubit will interfere with others. Any single qubit quantum gate can be visualized as a rotation of the state vector to a new position on the sphere's surface. This geometric model is essential for understanding how we manipulate quantum information before measurement. When we measure a quantum system, we are performing an act of destruction. Superposition is fragile. The moment we observe a qubit to see if it is 0 or 1, the wave function collapses. This is not a failure of our equipment, but a fundamental postulate of nature. The Born rule tells us how to predict the result. If our qubit is in state psi and we measure in the computational basis, the probability of seeing outcome 0 is the square of the magnitude of the ket 0 component. This means that quantum computers do not provide a single deterministic answer in one go. Instead, they provide a probability distribution. To get the correct answer with high certainty, we must design our algorithms to ensure the correct answer has the highest probability, and then we run the computer many times to sample the results. If superposition is the state of quantum computing, interference is the engine. Think of a quantum calculation as a series of ripples on the surface of a pond. As these ripples move and interact, they can build on each other. This is constructive interference. Or they can cancel each other out. This is destructive interference. A quantum algorithm is essentially a carefully choreographed sequence of operations that uses interference to delete all the wrong answers to a problem. By the time we perform our final measurement, we have ensured that the probability amplitudes of the incorrect paths have canceled out to nearly zero, while the amplitude of the correct path has been amplified. This is the secret to quantum speedup. We don't just check every answer in parallel. We use interference to ensure only the right answer survives the collapse. Einstein famously called entanglement spooky action at a distance. It describes a situation where two qubits are so linked that you cannot describe one without the other. If we have two entangled qubits, measuring one instantly determines the state of the second, even if they are on opposite sides of the galaxy. In quantum computing, entanglement is not just a curiosity, it is our primary resource for connectivity. It allows us to create a shared computational space where n qubits can hold 2 to the n bits of information in a single collective state. However, there is a fundamental limit, the no-cloning theorem. Because measuring an entangled state collapses it, it is mathematically impossible to create an identical copy of an unknown quantum state. This makes quantum data very different from classical data. You can't simply Control-C, Control-V a qubit.
To build a quantum program, we use gates. These are the instructions we give to the hardware. The Pauli X gate is the quantum NOT gate. It flips a 0 to 1 and vice versa. The Pauli Z gate is more subtle. It doesn't change the 0 or 1 value, but it flips the sign of the phase, which is crucial for interference. The most essential gate is the Hadamard, or H gate. It takes a definite state like 0 and rotates it exactly to the equator of the Bloch sphere, creating a 50-50 superposition. By applying an H gate to every qubit in our computer, we can prepare the machine to check every possible input to a problem simultaneously. To perform complex logic, qubits must interact. The most common interaction is the C0 gate. It involves two qubits, a control and a target. If the control qubit is 1, the target qubit is flipped. If the control is 0, nothing happens. The magic happens when the control qubit is in a superposition. In that case, the C0 gate doesn't just check the control, it entangles the two qubits. By combining C0s with single qubit gates, like Hadamard and T, we can build a universal gate set. This means we can perform any possible quantum calculation, much like how a classical computer uses NAND gates to build everything from spreadsheets to video games. One of the most powerful subroutines in all of quantum computing is the quantum Fourier transform, or QFT. Just as a classical Fourier transform finds the frequencies in a sound wave, the QFT finds the periodicities in a quantum state. The QFT is exponentially faster than the best classical Fourier transform. We use it as a core component of quantum phase estimation, or QPE, which allows us to find the phase or energy of a quantum state with incredible precision. This is the engine inside Shor's factoring algorithm and molecular simulations. It allows the quantum computer to see global patterns in data that a classical computer would have to check one by one. Shor's algorithm is the killer app of quantum computing. It solves the problem of factoring large numbers exponentially faster than any classical machine. Modern encryption, like the RSA that protects your bank account, relies on the fact that while multiplying two large primes is easy, finding those primes from their product is nearly impossible. Shor's algorithm bypasses this by reducing the factoring problem to period finding. By using the QFT, the quantum computer can find the mathematical rhythm of a number's factors in a single massive interference step. If we had a large enough quantum computer today, it could break almost all of the Internet's current security in a matter of seconds. While Shor's algorithm gives us an exponential speedup, Grover's algorithm gives us a quadratic speedup. It is designed for searching an unsorted list. If you have a list of n items and only one is correct, a classical computer must check every item one by one. For a list of 1,000,000 items, that's 1,000,000 checks. Grover's algorithm can find the item in just 1,000 steps, the square root of n. It works by using an oracle to flip the phase of the correct answer, and then a diffusion operator to pump the probability away from the wrong answers and into the right one. It is incredibly versatile and can be used to speed up everything from drug discovery to cracking passwords.
We are currently in the NISQ era, noisy intermediate scale quantum computing. Today's qubits are too noisy to run long algorithms like Shor's. Instead, we use variational algorithms. These are hybrid programs. A quantum computer prepares a state with tunable knobs, parameters, and a classical computer measures the result and tweaks the knobs to find a better solution. This variational quantum eigensolver, VKE, is exceptionally powerful for chemistry. It allows us to simulate how electrons move in a molecule by training the quantum computer to find the lowest energy state, much like how you might train a neural network. As we scale up variational algorithms, we hit a mathematical wall called barren plateaus. In a learning problem, the classical optimizer tries to navigate a landscape of peaks, bad solutions, and valleys, good solutions. However, as we add more qubits, this landscape often becomes a flat, featureless plane. The optimizer has no gradient to follow. It doesn't know which way is down to the valley, so it gets stuck. Recent research has used Lie algebra to prove that this happens when our circuits are too generic. The key to avoiding these plateaus is specialization, using circuits that are carefully tailored to the specific geometry of the problem. How do we actually build these machines? The most famous approach uses superconducting transmon qubits, favored by IBM and Google. These are tiny electrical circuits on a silicon chip that behave like artificial atoms. Because they are lithographically made, we can use existing semiconductor factories to build them, which is a huge advantage for scaling. However, because they are effectively man-made atoms, no two are perfectly identical.
We must carefully tune them with microwave pulses and keep them in a dilution refrigerator at 10 millikelvin to prevent the electrical resistance from destroying the quantum state. An alternative approach is to use nature's perfect qubits, individual atoms. Trapped ion systems, like those from IonQ, use electromagnetic fields to hold a chain of ions in a vacuum. Neutral atom systems, like QERAs, use focused lasers called optical tweezers to arrange rubidium atoms in a precise grid. These atomic systems have a massive advantage. Every atom of the same element is identical. They don't have the manufacturing flaws of superconducting chips. They also have all-to-all connectivity. Any ion in the chain can talk to any other ion using vibrational modes, which eliminates the need for messy swap gates. If you've seen a photo of a quantum computer, you've seen the chandelier. This is actually a dilution refrigerator. Its job is to cool the quantum processor down to near absolute zero in several nested stages. Each stage is wrapped in mu-metal shields to block out the Earth's magnetic field and Faraday cages to block out Wi-Fi and radio signals. We even use specialized Sty-cast epoxy coatings to absorb infrared radiation from the warmer parts of the machine that would otherwise melt our qubits. The cabling is another nightmare. We have to run hundreds of high-speed coaxial cables from room temperature down to 10 millikelvin without letting any heat leak in. To reach the fault-tolerant era, we need quantum error correction, QEC. Since we cannot copy qubits, we use a trick. We encode one logical qubit across many physical qubits. The leading method is the surface code. We arrange qubits on a checkerboard. The data qubits hold the information, while auxiliary qubits perform parity checks on their neighbors. These auxiliary qubits give us a syndrome, a map of where the errors are, without us ever having to look at the data and collapse it. If we can keep our physical error rates low enough, we can build a computer that is thousands of times more reliable than its individual parts. Programming a quantum computer is not just about writing gates. It requires a stack of software. At the top, you write high-level code in Python or C++. This is converted into quantum assembly, which is the low-level language of gates. But the hardware doesn't know what a gate is. The transpiler must rewrite your code to fit the specific chip's layout. Finally, the control software turns those gates into actual analog microwave pulses or laser flashes. In the NISQ era, we often need to hack the pulse layer to get the best performance, bypassing the gates entirely to implement custom noise-resilient controls. Because a quantum computer could break current encryption, the world is moving to post-quantum cryptography. PQC, NIST has already finalized several new algorithms that are resistant to both classical and quantum attacks. These are based on quantum-resistant math, like lattice-based problems, which are so complex that even a quantum computer cannot solve them efficiently. Organizations are advised to start switching now because of harvest now, decrypt later attacks. Bad actors are stealing your encrypted data today, waiting for the day they have a quantum computer to read it. Where is the industry heading? We're moving through three main phases. Right now, we're in Phase 1, demonstrating NISQ utility, where quantum machines tackle niche problems in finance and chemistry. Phase 2, arriving within the next 3 to 5 years, will see the first stable logical qubits, giving us error-corrected machines with 10 to 100 high-quality qubits. By phase 3, expected in the 2030s, we will have large-scale systems with thousands of logical qubits, finally achieving commercial advantage across the entire economy. You don't need to build your own. You can access these machines through the quantum cloud. To summarize, we're living through the second quantum revolution. We have moved from just understanding quantum mechanics to engineering it. We've explored the mathematical beauty of Hilbert spaces, the spooky power of entanglement, and the engineering reality of dilution refrigerators. Quantum computing is not just a faster processor, it is an entirely new tool for discovery. Whether it's developing new medicines with VQE or securing our data with PQC, the quantum era will redefine the boundaries of what is computable. As you continue your studies, remember, the goal is not to replace classical computers, but to complement them, solving the problems that nature itself intended for quantum systems.